Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 2 for our MCAT Organic Chemistry playlist, and this chapter is titled Isomers. In this chapter, we're going to cover the following objectives. First, we're going to discuss structural isomers, which have the same molecular formula, but they differ in how their atoms are connected. These differences can significantly affect the physical and chemical properties of the compounds. Next, we're going to dive into stereoisomers. We're going to break this category into two main types: conformational isomers, which result from rotations around single bonds, and configurational isomers, which cannot interconvert without breaking and reforming bonds. As part of this, we're also going to discuss how to assign R and S designations to chiral centers. Finally, we will examine relative and absolute configurations. We're going to explain how the E and Z system is used to describe double bonds and how to interpret Fisher projections, which are particularly helpful for visualizing stereochemistry in biomolecules. With this introduction, let's go ahead and get started with structural isomers, also known as constitutional isomers. These are compounds that share the same molecular formula, meaning they have the same number and types of atoms. However, the way these atoms are connected is different, and this variation in connectivity leads to differences in physical and chemical properties. For example, let's take the molecular formula C6H14. Several structural isomers can be drawn for this formula as shown here. If we wanted to figure out these structures, we can do this systematically. The first step is to start with the longest carbon chain possible. For C6H14, this would be a straight chain alkane with 6 carbons. And that's going to be called hexane, where all 6 carbons are connected in a row and the remaining hydrogens fill the bonds to satisfy the valency of carbon. This is the simplest structure. Next, we shorten the carbon chain by 1 and create a 5-carbon chain. With a 5-carbon chain, we now have 1 carbon left over, which we can place as a substituent. And this substituent is specifically a methyl group, where the placement of the methyl group gives us unique structures. For example, if the methyl group is attached to carbon 2, we get 2-methylpentane. If the methyl group is placed on carbon 3, then we get 3-methylpentane. An important note here is that if we try to place the methyl group on carbon 1 or on carbon 5, this doesn't create a new structure because those placements are equivalent to hexane when it's rotated. Similarly, if we try to place the methyl group on carbon 4, it would actually be the same as placing it on carbon 2 because we always number the chain to give the substituent the lowest possible number. And this rule ensures that we don't end up naming the same structure twice under different conventions. Now let's shorten the chain again to 4 carbons. This gives us a butane backbone. This also gives us 2 carbons that we can place as substituents to get unique structures. If we were to place both methyl groups to the same carbon, specifically carbon 2, then what we would get is 2,2-dimethylbutane. If we wanted to place one of the methyl groups on carbon 2 and the other on carbon 3, then we would get 2,3-dimethylbutane. So now we have a total of 5 unique structures that all have the same molecular formula, C6H14. From here, if we try shortening the chain further to 3 carbons, meaning a propane backbone, we will have 3 leftover carbons to distribute. However, any way we arrange them, we actually end up recreating the structures we've already identified. Therefore, we have accounted for all of the possible ways to arrange the carbon skeleton while keeping the molecular formula C6H14. Now, if the molecule contained one or more functional groups instead of just being a simple hydrocarbon, we're going to follow the same steps. You're going to start by identifying the longest carbon chain. Then you're going to systematically explore all unique arrangements of the functional groups to determine all possible constitutional isomers. And throughout this process, you want to make sure that each carbon satisfies its valency of 4 bonds, and you account for all of the attached hydrogens. Now that we've covered structural isomers, I want us to take a step back and look at the bigger picture of isomer classifications. Isomers, by definition, are molecules that have the same molecular formula, but different chemical structures. The first question to ask when you're classifying isomers is, do they have the same connectivity of atoms? If the answer to that question is no, then we're dealing with structural isomers, also known as constitutional isomers. Just like we discussed, these differ in how the atoms are connected, and that leads to entirely different arrangements of the molecule. But if the answer to that question is yes, meaning the connectivity is the same, then we're dealing with stereoisomers, and we move on to the second question. The second question is, do these molecules require bond breaking to interconvert between them? If bond breaking is required, then the isomers fall under the category of configurational isomers, which we'll break down further in just a moment. If the answer to that question is no bond breaking is required, then we have conformational isomers, which are different arrangements of the molecule that can be achieved by simply rotating around single bonds. Now let's go back to configurational isomers. These are isomers that cannot interconvert without breaking bonds. The next important question to ask is, are these isomers non-superimposable mirror images of each other? If the answer is yes, then we're looking at enantiomers, which are a type of stereoisomer that are chiral and mirror images of one another. If the answer is no, meaning that the isomers are not mirror images, then we're dealing with diastereomers. These are also stereoisomers, but they differ in spatial arrangement without being related as mirror images. Within diastereomers, we can further ask, do these isomers differ in arrangement around an immovable bond, such as a double bond or a ring structure? If the answer is yes, we classify them as cis-trans isomers, also known as geometric isomers. This can occur due to the restricted rotation around double bonds or within cyclic systems where substituents are either on the same side, cis, or on opposite sides, trans, of the molecule. This flowchart of questions helps us break down the different types of isomers, and it makes it easier to identify which category a specific isomer pair falls into. With this, we can move into objective 2, where we will focus on stereoisomers. Let's start with discussing conformational isomers. These isomers arise due to differences in rotation around single sigma bonds. Single bonds, they're free to rotate, but this rotation can lead to varying levels of strain depending on how the atoms are positioned relative to each other. This is an important concept because it explains how molecules can adopt different shapes without breaking or rearranging bonds. A common way to visualize these conformations is through Newman projections, which allow us to look down the axis of a carbon-carbon bond. In this projection, the molecule is depicted as two sets of atoms. One set bounded to that first front carbon, and another set bonded to this back carbon, with the bond between them forming the central axis. This view makes it easier to analyze how the groups around the bond are positioned relative to one another. With that being said, it's important for us to learn how to convert from bond line to Newman projections and how to convert from Newman projections to bond line. So let's get into that. For example, if we start with the following bond line structure, we can go ahead and convert it into a Newman projection following a couple of steps. First, we want to identify the bond we're going to look at. In this case, it's this central carbon-carbon bond as indicated by the eye. Next, we want to observe the front and back carbons as separate planes. The front carbon is represented by a dot, while the back carbon is represented by a circle around it. Third, we want to look at the substituents around each carbon. We'll start with the front carbon. We see that this front carbon has a chlorine substituent that's pointing up. There is also a hydrogen there that is not explicitly drawn in bond line. This hydrogen will be pointing up as well, since the angle of the bond right here is pointing relatively up. Finally, we have this methyl group that's pointing downwards. So with this, we draw the following structure: a central carbon with a chlorine substituent pointing up and a hydrogen pointing up, and then our methyl group here pointing down. Then we're going to do the same for the back carbon. So let's look at the back carbon here. In this back carbon, we have a bromine group and a hydrogen pointing down and a methyl group pointing up. With this information, we can draw the following structure: our back carbon with the bromine and hydrogen substituents pointing downward and the methyl group pointing upward. Finally, we take our structures for the front and back carbon and overlay them to get the Newman projection. With this, we now know how to go from bond line to Newman. But what about the other way around? In the reverse process, where we convert a Newman projection back to a bond line structure, we need to do the following. First, we want to identify the front and back carbons in the Newman projection. The dotted carbon is the front carbon, and the circle is the back carbon. Next, we want to translate the substituents around each carbon into their corresponding positions in the bond line structure. Essentially, we're just going to move the front and back carbons apart, and then we're going to draw a bond between the front and back carbon. Last, we want to recreate the molecule properly. This means we need to replace the dot and the circle with the standard bond line representation of carbons. We also want to draw out the substituents properly. And then finally, make sure to clearly distinguish between substituents that are above, below, or in the plane relative to the carbons, because these are going to affect the overall 3D structure. So here we have our front carbon, and here we have our back carbon. In our back carbon, we have a methyl group pointing up and a chlorine substituent pointing down. So what you notice here, we have depicted that properly with the methyl group pointing up and the chlorine group pointing down. For our front carbon, we have an ethyl group pointing downwards, which we drew out fully, and an alcohol group pointing upwards. Remember, with bond line, we do not explicitly draw the hydrogens. So, now that we've explored how Newman projections help visualize conformational isomers, Let's dive deeper into conformational analysis. Conformational analysis involves evaluating the stability of different conformations of a molecule by examining factors such as torsional strain and steric interactions. These factors determine how favorable or unfavorable a particular conformation is from an energetic perspective. To fully understand the differences between conformations, we need to introduce two key concepts: dihedral angle and torsional strain. The dihedral angle is the angle between two planes, which in this case refers to the angle formed by bonds on the front and back carbons in a Newman projection. This angle helps define the spatial relationship between substituents on adjacent carbons. Torsional strain arises from the repulsive interactions between electron clouds in adjacent bonds. These interactions, they create energy differences between conformations, such as the relatively stable staggered conformation and the less stable eclipsed conformation. To better understand these concepts and their effect on stability, we're going to use butane as an example. So we're going to start with the bond line structure of butane and convert it into a Newman projection. For this, we will focus on this central carbon-carbon bond, and we're going to be viewing the molecule along this bond axis to simplify how we visualize its conformations. In the Newman projection, the front carbon is represented by a dot, and the back carbon is shown as a circle around the dot. The substituents, so the hydrogens and the methyl groups, they are arranged around these carbons to reflect their spatial arrangement in 3 dimensions. So this is our starting Newman configuration drawn to represent this bond line structure of butane. Next, we can rotate the molecule around this central bond and then examine the different conformations that arise. Each rotation changes the dihedral angles between substituents on the front and back carbons, and this is going to impact the molecule's energy and stability. For butane, as we rotate the bond in 60-degree increments, we're going to observe 4 key conformations that can be visualized on the plot of energy versus rotation. Let's go over each. In this first rotation, which is the Newman projection we just drew for butane, looking about this central carbon-carbon axis, we notice that the 2 largest groups, the methyl groups, are positioned opposite each other with a dihedral angle of 180 degrees. This arrangement minimizes both steric and torsional strain, making it the most stable and lowest energy conformation. Starting from this configuration, if we rotate the single bond by 60 degrees, we move into the first eclipsed conformation. So after a 60-degree rotation from the anti-conformation, now the groups on the front and back carbons align in such a way that a hydrogen overlaps with a methyl group, and the other substituents also overlap as well. In this conformation, the dihedral angle is 120 degrees, and the repulsion between overlapping bonds introduces torsional strain, and that raises the molecule's energy. So looking at our energy versus rotation plot, you notice that the eclipsed conformation is higher in energy than the anti-conformation, and you also notice that the anti-conformation is the lowest energy conformation. Rotating this eclipsed conformation by another 60 degrees brings the molecule into the gauche conformation. For the gauche conformation, the dihedral angle is 60 degrees, and the methyl groups are no longer opposite, but they're actually positioned next to each other. While this eliminates direct overlap, the proximity of the bulky methyl groups does create some steric strain, and that makes this conformation higher in energy than the anti-conformation, but lower in energy than either of the eclipsed conformations. From here, we're going to do another final 60-degree rotation, and that brings the molecule to the totally eclipsed conformation. At this conformation, the two methyl groups are positioned directly over each other. They are directly overlapping with a dihedral angle of 0 degrees. This creates the maximum torsional and steric strain, and it also makes it the highest energy conformation. So by rotating the molecule incrementally and observing the conformations, we see how the dihedral angle affects energy. This energy versus rotation plot helps us visualize the different conformations and where they stand energetically. So our anti-conformation is the lowest energy conformation, followed by gauche, followed by eclipsed, and then finally the totally eclipsed conformation. This is our highest energy conformation. Now, this information is really important, so I want to repeat and summarize. Conformational analysis allows us to understand the relative stabilities of different conformations of a molecule by evaluating the interactions between substituents. For butane, these conformations and their associated energy levels can be summarized in the following way. In the anti-conformation, the two largest groups, aka the methyl groups, they are positioned opposite each other with a dihedral angle of 180 degrees. This conformation minimizes steric and torsional strain, and it makes it the lowest energy and most stable conformation. Then we have our gauche conformation. The two largest groups are adjacent to each other with a dihedral angle of 60 degrees. The proximity of the methyl groups introduces steric strain, making this conformation less stable than the anti. Then we have our eclipsed conformation. The substituents here on the front and back carbons overlap, creating torsional strain due to electron repulsion. This conformation occurs at a dihedral angle of 120 degrees, and it is higher in energy compared to the anti or gauche conformations. Then, our final conformation is the totally eclipsed conformation. Here, the two largest groups, the methyl groups, directly overlap with a dihedral angle of 0 degrees. And this creates the maximum steric and torsional strain, and that means it is the highest energy conformation, also the least stable conformation. Now let's move on to cyclic conformations. Ring systems are fundamental in organic chemistry, and understanding their conformations is also important for predicting their stability and reactivity. Cyclic molecules experience something called ring strain, which arises from three main factors. The first factor is angle strain. This occurs when the bond angles in a ring deviate from their ideal bond angles. So if the angles are compressed or stretched, then strain is introduced into the molecule. The second factor is torsional strain. This is caused by eclipsed or gauche interactions between bonds in the ring, and that leads to electron repulsions and increased energy. Finally, we have our third factor, which is non-bonded strain, also called steric strain. This results from non-adjacent atoms or groups crowding into the same space and causing destabilizing interactions. To see how cyclic molecules minimize these forms of strain, let's take cyclohexane as an example. Cyclohexane is a highly studied cyclic molecule because it can adopt multiple conformations to reduce strain. Among these conformations, we have the boat and the twist boat conformations, which are less stable because they introduce torsional and non-bonded strain. This is in comparison to the chair conformation that cyclohexane can adopt. This is more stable and more significant. It minimizes angle strain by maintaining nearly ideal bond angles and reducing torsional strain by staggering the bonds. In the chair conformation, which we're going to focus on, we observe two types of substituent positions, axial and equatorial. So let's discuss what both of those mean. Each carbon atom in the chair conformation has these axial positions which point either vertically up or down, and they're going to alternate around the ring. To determine whether the axial position at a specific carbon points up or down, you want to follow the direction of the carbon's bond angle in the ring. If the carbon's angle points upward, then the axial substituent is going to point up. And if the angle points downward, then the axial substituent will point down. The other position is the equatorial position. These point outward roughly along the plane of the ring, and they alternate from slightly up or slightly down around the ring, and they're always in the opposite direction to the axial position at the same carbon. This arrangement means that at each carbon in this chair conformation, one substituent occupies an axial position, either up or down, and the other occupies an equatorial position that's outward in the opposite direction. So for example, if a substituent is axial up at a given carbon, then the equatorial position at that carbon will point outward and down. This alternating pattern extends around the whole ring. So if the axial position at one carbon points up, then the axial position at the next carbon will point down, and so on and so forth around the ring. Similarly, the axial positions alternate to complement the axial pattern. So if the substituent is axial up, then the equatorial position is going to point outward and down, and then that's going to alternate around the ring. And this way, this altering arrangement is going to help minimize strain and stabilize the molecule. To reiterate, cyclohexane adopts a chair conformation where each carbon has an axial and equatorial position. Now, when substituents are added to cyclohexane, their placement significantly impacts the molecule's stability. Substituents, they prefer the equatorial positions whenever possible because this minimizes non-bonded strain, particularly steric interactions with axial hydrogens. For instance, a bulky substituent like a tert-butyl group in the axial position, that's going to create destabilizing 1,3 diaxal interactions. And these are steric clashes with other axial hydrogens on the same side of the ring. But if we were to move that bulky group to the equatorial position and put it right here, for instance, then our chair conformation is going to be more stable. Moving the bulky group to the equatorial position eliminates these interactions and makes the molecule more stable. In addition, cyclohexane is also dynamic and it can undergo something called a ring flip. During a ring flip, the chair conformation inverts. And it inverts and causes all of the axial substituents to become equatorial and all of the equatorial substituents to become axial. This process is important because it allows the molecule to adopt the conformation with the lowest overall energy. The more stable conformation is the one where the bulky groups occupy equatorial positions and thereby reducing steric strain. That leads us into our next topic on configurational isomers. But for today's video, we're going to end right here. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.